for tuning in. It is my pleasure to get a chance to tell you today about my work that I've done over the past 3 years as a Lawrence Fellow, giving us kind of a new way of thinking about time resolve or DFXM through the lens of kind of a time resolved picture of these defects and deformations we're looking for. So I come at these projects or experiments from the perspective of someone trained in ultrafast, giving us kind of a different picture of the same type of view. So my story today will be split into three chapters. I'll start by focusing in on the questions that we have of dynamics, specifically at the mesoscale in these defects. And then I'll turn to kind of explaining the infrastructure that I've developed, both optical as well, X-ray as well as the kind of interpretation and analytical methods to be able to use time resolved DFXM. And then I'll turn to kind of a first study that I did on kind of a detailed view at the or at the single dislocation level of subsurface of the highest temperatures in annealing. So without further ado, as many of us well know, lattice defects set really important material behaviors across many different applications. For example, as we see in phase transition materials like the ones many of you will have in your random access memory of your computers, we find that defects are involved both in the mechanisms that seed and nucleate those transformations. In yet other types of materials, like structural materials, we find as we start to apply pressure to the material, those stresses ultimately localize, giving rise to these three-dimensional networks of defects that in some cases cause materials to strengthen, while in other cases they cause the materials to fail, often through very specific mechanisms. And in yet other types of systems, we find that or large populations of either point defects or grain boundaries can be used to continuously tune the electronic or thermal properties of a material. So to be able to optimize both the efficiency and performance of these types of materials, we need to be able to both understand and control how these defects occur across many length scales. As we start to zoom in on this challenge, we can immediately see why this actually exemplifies kind of a grand challenge problem, linking kind of chemistry, physics, mechanics, and material science, as to be able to connect these single individual defects at the atomic scale all the way to the continuum properties that we require for our kind of engineering models to be able to build up these larger scale components. We find 10 orders of magnitude in length scale with a commensurate 15 or more decades of timescales. The challenge in this problem lies in describing this incredibly high dimensional problem at the atomic scale, coarsening the information content while still capturing the appropriate relevant physics to be able to, by the time we get to this continuum length scale, still have a representative model that is true to the physics that we see. This kind of describes what we understand and know very well as the mesoscale problem in materials science. In metals, these types of multiscale or mesoscale dynamics are driven primarily or largely by the dynamics of dislocations that are characterized by three principal vectors that define them. So the dislocation line vector, Berger's vector, and slip plane normal. So when we zoom in a little bit more on how exactly this multi-scale behavior of dislocations work, we find that dislocations actually pack into different types of preferential patterns based on the local or subtle changes in those local conditions. As we've heard about earlier in this workshop, dislocations can pack into different types of structures, giving rise to very different types of macroscopic behavior. For example, they can pack into stabilizing grain boundaries, giving rise to things like strength, or they can start to pile up and localize residual stresses, ultimately, in some cases, leading to fracture or failure of the materials. So to be able to refine and control these macroscopic properties, we really need to be able to understand how these dislocation structures both form and evolve. However, many of these processes can't actually be measured by experiments presently. So the most established and kind of long-standing tools for this type of characterization at the single dislocation level lie in electron and force microscopy that can resolve at the atomic scale single dislocation cores. But zooming out a little bit more, we can start to look at the dislocation line vectors and how they pack into a crystal at kind of hundreds of nanometer length scales. And more recently, groups have started to time resolve the electron microscopes, giving us these movies of how dislocations navigate through fields of obstacles. However, ultimately, what we find is that electron and force microscopy both have significant limitations, both in the field of view they can actually measure with this higher resolution and sensitivity, well, resolution specifically, as well as the fact that they really can only measure surfaces or thin films. So, what does this mean? Well, this means that, of course, our understanding of how dislocations behave at this level, deep inside of materials, is really limited to models and indirect measurements. So, this really means that we have an incomplete understanding of many different types of macroscopic processes. So, this kind of motivates my interest and many other people's interest in developing the time resolved tools for this type of bulk material deep beneath the surface. So now I turn to time resolved DFXM to give us kind of a new view of this type of time resolved version. So as everybody who comes before me has already explained, DFXM gives us a really nice opportunity to, in real space, collect an image of the subtle distortions deep inside of the lattice in transmission mode with an X-ray objective lens along that lattice plane that allows us to see how these distortions span spatially. Indeed, by coming in with a line beam, we can illuminate a sheet or define our observation plane with limited integration, simplifying our interpretation and giving us this detailed view with tens to hundreds of nanometers of resolution covering hundreds of microns. And because we come in with a monochromatic and nearly collimated beam, it affords us an incredibly high sensitivity to lattice displacements, making the apparent size of any of these defects or dislocations quite a bit larger than we would normally expect to see them in other types of measurements. So in classical DFXM, as other people have discussed before me, we tune the diffraction condition, either moving the detector up and down through 2 theta or rotating through the rocking curve of the crystal. And we, at each point along those scans, collect an image showing the spatial extent of that specific deformation field. Um, and then we reconstruct those, hundreds or thousands of images into these higher dimensional maps that show us the axial strain, orientation, and other types of parameters about that specific lattice plane. But you'll notice, of course, that for this map to really be representative of the system, all of these hundreds or thousands of images all need to collect information about exactly the same crystal, unchanging completely in time. This imposes a very strict static necessity that this be a completely static measurement. In my work, I've kind of gone that next step, looking instead at kind of keeping the entire microscope fixed, looking at one single distribution of deformation fields, and instead watching how that evolves as a function of time. As a result, this has given me kind of this access to time-resolved views of how these patterns of dislocations move and evolve hundreds of microns beneath any surface, deep inside of single crystals. So I will focus for today's talk on single crystal studies, for which we can now start to puzzle out a lot more detail about what we're seeing in these dynamics. But of course, as many of you know quite well, when we are kind of developing this new tool, we don't actually have a rule book to build the microscope or interpret the results. So the reason that this has taken 3 years is because we had to start by developing the infrastructure needed to use it. So the first step was to design and implement the optics. I'm sure most of you are quite familiar with the ID6 configuration, so I won't belabor this. But I began these DFXM experiments at ID6 using kind of the stroboscopic imaging tools that we had installed there to be able to explore kind of this millisecond to second timescale that is characteristic of equilibrium dynamics in these materials. But then I took the next step, as there are a lot of deformations that happen much faster than this, and even at timescales that are inaccessible with synchrotron radiation. So then I went to the PAL XFEL in Korea and installed the first ultra-fast version of DFXM to collect images that show us kind of this deformation field over 32 femtoseconds in time with kind of a more of a pump probe type of a geometry. So now we have access to 13 orders of magnitude and timescales. So now we'll give ourselves a check and move on to the next question, which is, of course, now that we can collect these beautiful images, how do we understand what we're looking at? Because, of course, reciprocal space is a big place, and we're only sampling it at one single distribution. So to answer that question, we looked specifically at kind of a deeper look at the contrast mechanism here. So we started off looking at the schematic, asking ourselves what exactly is the physics that defines a signal in these DFXM images, and that corresponds to classical X-ray diffraction, so sensitivity to the local crystal structure and incident X-ray beam. But it also is a classical one lens or one objective imaging system, giving us a sensitivity to the imaging optics, so the aperture of the CRL and the detector optics and any aberrations therein. So, armed with this knowledge, we set out and built up the formalism for DFXM contrast to be able to describe kind of in an analytical form how the intensity on every single position on our detector corresponds to a convolution of the materials response and the instrumental specifications. So, we modeled the materials response with a micromechanical model using the deformation gradient tensor to describe the local deformation content at each point in our lattice, kind of based on how that defect spatially emanates. And then we look to the instrumental specifications and we define that using kind of a classical instrumental resolution function, which kind of ignores the diffraction condition and just defines for us the Q components that DFXM should be able to measure if everything was in the Bragg condition based on only the optical setup that's present. So with this knowledge, then we were and model, we were able to, or I guess we are able to now simulate for a given microscope geometry that we know very well because we set it up. What the say a well-defined 110 edge dislocation should look like in this configuration, and so this now allows us to qualitatively compare the data that we collect, showing these little dislocations moving around, to the simulations to be able to verify that we really understand what we're looking at. But it also then allows us to go a step further because it allows us now to think about how exactly we want to be able to look at these dislocations. So as we understand, reciprocal space is a big place, and we can change how we sample reciprocal space by rotating the crystal or changing kind of our diffraction condition to be able to change the contrast mechanism and therefore tune the way that we're sensitive to these dislocations. This is actually also very important in understanding whether we live in the dynamical diffraction limit or the kinematic diffraction limit. So for example, if we sit right in the center of reciprocal space of our little peak, then what we find is we're in what's called the strong beam condition. This means that we see every single defect that's present as a little shadow that moves around. And I have a movie here showing you some much more recent data on kind of a little subgrain of aluminum. And you can see all of these little dislocations moving around, a dislocation boundary here. And we can see, yes, that they're present, but we don't necessarily get such great contrast on it. But if we wanted instead to be able to zoom in specifically on only the dislocations, we could instead look at the edges of this peak in reciprocal space. This is called the weak beam condition. And now we can start to get a movie that looks something like this, where the little bright blobs correspond to kind of the anomalous scatter from the edges of the Bragg peak that are only scattering and in the scattering condition because of the large deformation content surrounding the dislocation cores. So now that we kind of are armed with this theory, both to interpret the results and kind of design our experiments around what we're looking for, now we have our check on interpretation, but we turn to this question of, great, now we can understand qualitatively what we're looking at, but to be able to inform those bulk models, we really need a quantitative understanding of not just one single dislocation, but of the large statistical populations of them that we collect in each one of our movies. So for that, we now turn to computer vision, as indeed these little dislocation objects are not actually single nice little blobs, but are kind of these more complex and intricate shapes, which have both dark and bright features on them, each of which are important to be able to encode the information about what this dislocation actually is. So to do this, we developed a customized workflow that starts with a stationary wavelet transform, specifically the Dobeshi's 4 orthogonal wavelets, where the third order detail coefficient gives us a map that looks something like this, where each one of these bright blobs basically just shows us that there is a dislocation present there in those pixels in the original image. So this now gives us a map to be able to find the bright components of each of these dislocations. For those of you less familiar with wavelet transforms, they're a little bit similar or analogous to a Fourier transform, although the mathematics is fairly different. So ultimately, what this allows us now to do is to find the bright components of each of these dislocations. But of course, we need both the bright and the dark components. So now we use a region-based segmentation method to identify the dark component as well. So now that we can identify the bright and dark components, we have the entire dislocation object along both kind of pieces of the feature. So now we can collect this for our entire stack of images in our movie, say several hundred, if not thousands. And now what we find is, of course, that in many cases, some of these dislocations in their deformation fields actually overlap partly. This actually makes sense, though, because from elastic theory, we understand that the way that dislocations interact is via their deformation fields. So in all the places that the dislocations are doing some of their most interesting things, they will actually be apparently overlapping in this picture. So we use a Kelman filter here, which is based on, in this case, kinematic motion. But we can change the model to include the representative physics for this type of defect motion. And it predicts for us and validates the position of each of these dislocations in places where they are apparently overlapping in part of the feature. So now we collect the position of each of these dislocations for our entire series of images in the movie. And what we find very quickly is that the last step is that we now need to be able to assign the identity of each dislocation to be able to track them for the entire thing. So for this, we use the Munkres method, which assumes a minimum distance traveled per frame. And what we now have is the ability to collect these traces that show us the position projected along each of the representative directions. So in this case, climb and glide. What the positions of each of these dislocations is for some arbitrary duration of a scan. So now that we have our ability to watch and track these dislocations, much more recently, we have been developing a Bayesian inference model to be able to combine kind of our identification of where that dislocation is and what it should look like based on elastic theory, and give us the ability to now automate the dislocation, both position and assignment in these DFXM movies to be able to really give us a pipeline to go from this raw data that we collect to the results in statistically significant amounts afterwards. But you'll have to stay tuned for that paper because it's coming soon. So now we get our nice check mark on these analysis methods. And now at long last, we are ready to study these types of dynamics. So here I turn to my first study that I did in 2018, looking at kind of this first detailed view at the single dislocation of annealing deep inside of single crystal aluminum at the very, very highest temperatures. So I'm not going to belabor what annealing is at this point. I think a lot of the people who have come before me have done a great job. But suffice it to say that annealing is important in industrial processing and ultimately tunes the properties of a material based on the dynamics of dislocations at many different length scales. When we look at what this looks like at kind of a comparison between continuum and microstructure, we can see that as we increase the temperature, what actually happens at the single dislocation level should be that as the point defect density increases, commensurately, as we add more energy, we are also now starting to be able to mobilize sessile or pinned immobile dislocations, allowing now new pathways for interaction as well as new new versions of kind of annihilation or dislocation simply leaving the crystal. So annealing has been studied quite extensively, but we still have a lot of uncertainties deep beneath the surface. And I'll focus for today at the very highest temperatures where theory predicts that we should actually have classical dislocation dynamics starting to break down into these more exotic types of dislocation interactions that give rise to more exotic types of variation in the microstructure. However, we haven't really had the tools to be able to see how this happens. So I'll focus for today on one scan that I did of single crystal aluminum deep inside of an optical furnace that I have shown here. And this was kind of a 12-hour scan that we took. I'll focus though on the top kind of 7% of temperature to the melt, where we increase the temperature only by a couple degrees Celsius in each step every 2 to 5 minutes to be able to increase the temperature and watch the system equilibrate to the new temperature. And so before I show you all the action-packed movies, I will remind you what we're actually watching in these movies, which is three-dimensional networks of these dislocations that are being sliced by our observation plane, giving us these movies that encode just that slice through the structures that are moving in and out of the plane or through the plane. More recently, and I unfortunately don't have time to go into too much detail about this, more recently we've started doing 3D maps in the weak beam condition of these 3D dislocation structures. And so this shows you very concretely how, this is a real map of the dislocation structures in single crystal aluminum after annealing. And this green plane shows you exactly what we're taking in these movies. So now looking a little closer at what these movies are, you'll see at 93% of the melt that we see nothing very substantial. And this actually is indicative of the beginning of this process that we will ultimately be looking at, as this breathing motion of the features actually encodes information about dislocation structures that are just beyond our resolution and sensitivity in this particular format. However, as I increase the temperature very quickly, I saw this coarsen into single dislocation objects that are indeed discrete, and we can watch how they pack either into grains or into dislocation boundaries. And you'll notice here that indeed these dislocations are moving around in this stop and go kind of jerky fashion. This is actually incredibly characteristic from TEM experiments of kind of how dislocations move around through a field of obstacles. However, at the very highest temperatures, we saw something very different. I started to see how these dislocations now start to move around and almost flow through each other unobstructed. So the question that I'll focus on for today's talk is, what exactly are the dislocation behaviors that are characteristic of these temperature regimes? And to answer that question, I'll focus in on the dynamics of each of the component dislocations that comprise this single dislocation boundary here. And we'll look at the regime that we can actually resolve this at the single dislocation level, going from 97 to 99% of the melt. So that takes us from the interaction to the flow regime. So now, since we have an FCC crystal here that is very well known and well studied, as well as a forward model to be able to compare this to, we understand that, or we can identify now that these actually correspond to edge dislocations of the 1 minus 1 Burgers vector that pack into a tilt boundary, which is a stabilizing dislocation structure. So what this allows us to do now is to build up a crystallographic model that shows us the Burgers vector, line vectors, and slip plane normals, and allows us now to project that onto our imaging plane, showing us now the directions that are characteristic of motion of each one of these dislocations along the climb and the glide directions. This corresponds to kind of the lattice level for the mechanism of dislocation motion that I have shown here in these movies, for those of you who might be a little less familiar with dislocation dynamics. So now that we understand how to link these movies back to the lattice level, we can now use these computer vision methods to uncover or unravel the positions of each one of the 11 component dislocations in this boundary over 10 minutes of timescales. And so now we can watch very concretely how exactly we go from this interaction to the flow regime. So we'll start looking at this interaction regime, and we'll begin with two separate snapshots. And we see very quickly that actually this boundary begins as two separate boundaries that are misoriented with respect to each other, as I have shown here, and then ultimately coalesce. So what you would normally do in an ex situ experiment, of course, is kind of come up with some theory as to why these might coalesce, and there's some good theory that you could compare this to. However, at this high temperature, we actually were able, or I actually was able to resolve exactly the event that catalyzes this coalescence. And this occurs as a nearby lone dislocation glides towards the boundary or the lower segment and ultimately inserts itself into the lower segment. This then causes all of the dislocations in the lower, less stabilized boundary to move around and rearrange until they ultimately get sucked up into the upper, more stably oriented boundary, giving us the coalescence that we see. So what does this show us? Well, in addition to showing us a very interesting and detailed mechanism for how this dislocation insertion occurs, this also shows us kind of the first view of this type of a fundamental kind of classical dislocation dynamics mechanism at 98% of the melt. This is a regime where actually there's a lot of theory that predicts that this shouldn't happen at this high a temperature because we should already be in the thermally dominated regime. So now we can go back to our roadmap here and say that, yes, actually from this dislocation insertion, we can see that this interaction regime is still characteristic of classical dislocation dynamics. But now we can go to the next question and ask ourselves, well, what exactly is happening in this flow regime? And to answer that question, it now helps us to go back to the movie. And we see that even though this is now only about 8 degrees Celsius higher in temperature, these dislocations are moving a lot more than the ones we saw in the previous movie. Indeed, classical dislocation dynamics would dictate that as we increase the temperature, we should see an increase in the mobility or the amount of motion of each of these dislocations. But what we see here is actually a much more dramatic effect. Beyond 98% of the melt, what we find is that the increase in the amount of motion of each of these dislocations, which encodes information about the mobility at a lower length scale, that the amount of motion that we see actually starts to scale exponentially in this kind of runaway behavior just at the edge of melting. So we can ask ourselves here, what exactly is changing about this boundary over this regime? So to answer that question, it now helps to go back to why this was a stabilizing boundary to begin with. And we can answer that question with some force field simulations. So we'll start looking at this lone dislocation, and with this kind of stress simulation, we can see that this lone dislocation does actually impart a fair amount of stress and corresponding strain onto the lattice surrounding it, spanning actually for about 5 or 10 microns, so long as we have enough resolution in force. Now, of course, we can integrate this over the corresponding volume, and this gives us a detail, or this gives us the strain energy cost that each dislocation imparts upon the lattice itself. However, when we start to now pack these dislocations along their slip plane normal, as we do for this dislocation boundary, what we find is an effect called stress screening. This ultimately is the dislocations interacting with each other as they're next to each other in an additive way, screening the amplitude and spatial extent of the strain fields that emanate from the dislocation cores, also creating an attractive force between these adjacent dislocations. However, as we increase the temperature now, we find that the spacing starts to increase and that these effects start to stabilize the boundary less and less. Only 4 degrees Celsius higher in temperature, we now see a very different story. We now can start to see competing forces interacting within this boundary as thermal mobility starts to amplify the random motion of dislocations out of the boundary, with lower attractive forces pulling them back in. And eventually what we find is that the thermal motion overcomes the more and more weakening dislocation boundary force until we eventually destabilize the boundary altogether. So what does this show us? Well, this now for the first time gives us a flagpole to be able to say, yes, this is where and what thermally activated or thermally driven dislocation motion really looks like, and what it looks like at the level of dislocation structures. So now, hopefully by now, I've been able to show you that with time-resolved DFXM, we have access now to a new regime of dislocation behavior, because we can now start to look at these long-range dislocation interactions and dislocation structures kind of giving us access to new regimes. I've shown you in this particular example how we can kind of move from classical dislocation dynamics at an unprecedented 98% of the melt, and we can watch how the thermal forces amplify until we eventually end up in a thermally dominated kind of structure just at the cusp of melting. And this gives us important insight into regimes that both models and experiments have historically really struggled to be able to access. So now to wind up, just to summarize, I've shown you today how kind of I've developed this new technique and infrastructure to be able to resolve dislocations at the single dislocation level, both the optics, the interpretation methods, and kind of the analysis methods to quantify this. And then I use this to show you a new view of dislocation structures at high temperatures. So now we have a new opportunity at our fingertips to be able to connect the microstructure directly to continuum dynamics in macroscopic materials. So now you can ask yourself, well, what's next? Well, next up is, of course, to find a way to connect the dots between those milliseconds and femtoseconds of timescales. So we have a whole bunch of exciting plans to extend this range of timescales. We also have some plans to start, actually we've already begun, developing methods with automation tools to automate the alignment of this dark field microscope to be able to now push us to more high throughput testing in this type of DFXM setup. And we also are working closely with our data scientists to define or refine the robustness of our analysis methods to be able to make it a robust tool across many different types of systems, as dislocations are not specific to single crystal aluminum. And we also have some plans and directions to install a laser system to be able to now start shifting towards kind of pump probe in situ testing. And so with that, I will acknowledge my very long list of collaborators for this very large scale project. And thank you all very much for listening. I'll be happy to take any questions.
Yeah, thanks very much for this very nice presentation. That was, I think, really impressive. I have now opened all screens I have for the participants and for also the people can see for questions. Is there any? No one currently raises a hand, so I could make a bit the icebreaker maybe after lunch. I work more in instrumentation, so my question is more in that field. Sorry. Your temporal resolution, I think, is limited because you either need to rock your detector or something else. Also, I just wondering if you would be able, because there were some prototypes from Japan of having several detectors in a line by optical coupling, if that would allow you to do single shot experiments.
So that sounds really interesting. What I would say is actually our limitation is not rocking. We don't rock the crystal at all. The only thing that limits us in timescale is the photon flux and the frame rate and the data transfer. The only being 3. So actually we already have done single shot imaging at the XFEL because we have 10 to the 12 photons per pulse. It makes it a little easier. The challenge of data transfer rates is a really tough one. We have some ideas for that, but the cost of the cameras go up exponentially.
Sure.
There's also an issue of shifting from stroboscopic measurements to kind of more of a faster timescale also eventually requires synchronization between the timing structure of the synchrotron and the control system at the beamline. So at XFELs, they're already set up to do that because most of the experiments at XFELs are pump probe type experiments. But I believe we're working towards that type of situation at ID6.
So nobody raises a hand. We have time for questions. People can. One is Wolfgang Ludwig has a question. Yes, Wolfgang, unmute.
Yeah, thank you for this very nice, impressive talk. Just a technical question also about the dimensions of your grain that you have been looking at and the geometry. Is it like, are you in transmission or in reflection mode when you do these observations?
So Grain is a little bit of a strong, a bold comment, and I say that because this is actually a full single crystal. So the grain inherently at lower sensitivity is 0.5 by 0.5 by 20 millimeters. But this particular subgrain is maybe a couple hundred microns in any dimension. And we picked that one kind of on a whim. We do find that, so we do measure in transmission mode, and we find, of course, that if you're in especially the strong beam condition, you end up with a very interesting interferometric imaging pattern because of the dynamical diffraction that occurs. And I think that there's a lot of, as someone who did interferometric imaging once upon a time in my PhD, I think that there's all sorts of interesting fruit to be had there, but it definitely introduces a more complex problem.
Thank you.
There's a second hand raising from Ashley. I think you can unmute yourself.
Thanks. Yeah, it's really great work. It's a lot to think about. I just, it's kind of a weird question, but I'm thinking Livermore. I'm sure that they're interested in annealing, but also some other things that happen very quickly to materials. What are the implications of these results for things like impact?
Yeah, so originally my Lawrence Fellowship was going to look at studying kind of the onset of plasticity during a shock wave. It turns out when you have a really, really complicated, highly sensitive microscope, and you're trying to, establish the microscope, shock physics is typically not the right first step to go to. So we started with a simpler system, and we still, one day we'll get to shock waves, but it's much further out. The issue becomes the faster the time scale, the more you're really flux limited. And going beyond, my estimate at this point is kind of a microsecond time scale. You actually need the XFEL because you simply can't get enough photons to be able to do this. But really, there are a lot of things. As soon as I started doing these experiments, it became very clear that there's a lot of interesting physics between, hundreds of milliseconds and femtoseconds. I also will, shamefully or shamelessly add that I will be starting a faculty position in a few months. So,
Congrats.
thanks. I say that also because this email address might not be valid if you want to get a hold of me after June.
I have another quick question if no one else's hand is raised. The interpretation stuff, are all those steps critically necessary, or were you just sort of doing a trial and error kind of thing, or like how did you go across that procedure or come across?
Good question. And I would say, as you did in your talk, I presented in a logical order, not necessarily in the order in which I did the experiments. So we started with the experiments and we saw all of this really exciting dynamics. And what we found very quickly is that with this sparsely sampled a region of reciprocal space, with only really one tiny little distribution of strain or deformation states, you really don't have enough information to be able to identify what most of the dislocations are. And so there was, a couple dislocation structures that we were able to tease out what they were based on the dynamics, but to be able to actually have access to larger scales, statistical distributions instead of the few little microstructures that we could actually understand, it became very clear that we needed a more detailed method. And from the data science perspective, this makes a lot of sense to develop a forward model because, of course, if you're trying to sample, I guess, well, not of course. So from the data science perspective, you can think about this as, a sparsely sampled problem that you don't actually have enough information to solve in an inverse way. meaning, you take the data set and you, just using that, solve out what the initial conditions must have been to get you there. But you don't actually have an infinite number of dislocations that could exist in any crystal. So you need to be able to constrain your system enough to be able to create a smaller sample set that actually has a unique solution for each one of these. And so that really requires a forward model to be able to train in the physics to a data science type of an approach. And so that was kind of the motivation behind it.
We have one question from the attendees, from Mustafa Khan. Can you speak, or do you need to use the chat, Mustafa Khan?
Can you hear me?
Yes, I hear you. Perfect.
So thanks for the great talk, Leora. I have a really fast question regarding the high throughput experiments. So in the plans of new ID3 beamline, they're planning to use planning to do this pink beam operation. Would it be possible to use single pulses of pink beam to do these time resolved experiments, or is bandwidth would not even allow that?
I think it should. The answer is that you have to, change the model to account for it properly. The place where you would do that is in the instrumental resolution function. But there's definitely an input for bandwidth, and so you can modify that and you're good to go. Now, I can't necessarily say whether you'd be able to see the dislocations with that bandwidth. I think the devil's always in the details, right?
Mm-hmm.
But there's no reason why you shouldn't be able to at least try this and see if it's a feasible thing. I think our estimates for being able to really do this in a reasonable way was that a bandwidth of kind of 10 to the minus 3 would be necessary, but that's from the perspective of an XFEL world where you have much higher coherence, so it changes the discussion a little bit because you're sensitive to bandwidth and coherence.
I see. Okay, thanks.
Mm-hmm. We can have a bigger discussion offline if you're interested.
Yeah, sure. That'd be great.
Absolutely.
I see a hand raising from Henning, but I see also the critical view of Carsten because of the timeline. So
let Henning go ahead.
Yeah, sure. Thank you. You're muted, Henning. Henning, can we unmute him?
Oh, yes,
when you increase the bandwidth of the contrast, of course, becomes deteriorates, and in order to see the strain around the dislocation, in that case, you may have to increase the spatial resolution. So these two things would go together: the spatial resolution and the pink beam, I think.
What I would add to that is, as we've started to explore different applications of DFXM, one thing that has become clear, especially with the time resolved variant, is that sometimes sensitivity doesn't really help you, especially in high deformation content materials. And so this is a place where actually a pink beam might be helpful to be able to see some intensity in more highly deformed structures so that you can start to kind of tease out those dynamics. But this is a longer discussion than a quick comment.
Okay, then I see no more hand raising in the neither in the attendees nor on the panel. So yeah, thank you again for the very nice presentation. It was a pleasure. We have one more talk on the agenda. It's an in-house